so apologies for the duplicate, right? So this presentation, this tutorial style of presentation, this is the third time I'm doing it, and I started with Kuwait City with the Mingog, and then I presented it in Sofia for a RIPE meeting over there, and this is the first time I'm doing that in Africa, and I'm very glad to do that. And this would be more or less the agenda. So I would like to do an introduction. The introduction would be very similar to the one of the other day. Just a couple of extra slides. And then I would like to tell you about a little bit about the architecture of the PMACCT software, and then bring you a couple of use cases. So one is about traffic matrices, which is very interesting because this is a peering forum, and there will be slides from the other day plus more slides also to review what is a traffic matrix and things like that. And then also an example totally different, which is like how to log traffic to files with PMACCT, and I will finish with the NetFlow or SFlow replication and horizontal scalabilities. So I will avoid to spend many words again on this slide. So that's me. I'm Paolo Lucente. I'm the author of PMACCT, and I work for NTT Communications at the moment, and that's my daytime job. And at night, during weekends and nights, I code PMACCT. This is in essence what the PMACCT software is about. So PMACCT would be that thing that is in the middle of this slide, in the orange bulb with the octopus. What you see over there is on the top left part of this slide, you see some red circles. So those would be data sources, yellow boxes that you see on the bottom left part of the slide. So like BMP, BGP, IGP. So BMP would be BGP monitoring protocol, GeoIP information with the MaxMind library, and also with the maps, so with external information. And the external information can be anything, right, that can be of interest, like, for example, correlating traffic flows to radius information, for example, right? So that would be an example. And then this information can be written into PMACCT supports a number of backends, like open source relational databases like MySQL, Postgres, SQLite, NoSQL databases like MongoDB or BerkeleyDB, but also flat files, memory tables, and brokers, so RabbitMQ and Kafka. And then you see that there are also some other boxes over there. So on the right side of the slide, so which are functions like probing, NetFlow, IPFix, and SFlow, and T replication. So, but we will review the use cases and where these come into play in the next slides. So, what would be a few of simple use cases for PMACCT? It's like you can read NetFlow IPFix and ingest it into PMACCT, and you can write that to flat files, and that would be PMACCT as a collector for flow telemetry data. The second would be like PMACCT collecting SFlow and replicating it. So that would be PMACCT as a replicator, like you point SFlow to PMACCT and you can replicate to actual collectors. A third example would be, for example, BMP, so the BGP monitoring protocol, or BGP itself pointed to PMACCT, or let's say with BGP establishing a peering relationship with PMACCT, and then this information is sent to a Kafka that will be PMACCT as enabler for analytics. And the fourth use case, very simple use case for PMACCT, it's reading like from a span port from a mirror port of a switch, for example, capturing this information with the libpcap library, and then this traffic is, PMACCT can make IPFix packets out of it, and that would be PMACCT as a probe. And then going to a little bit more complex use case, you can see this would be NFACCTD, this big orange circle, and that would be like one of the daemons, right? The NetFlow collector daemon, part of the PMACCT package. So you see you have NetFlow pointed at it, and then what NFACCTD can do with this traffic is, with one instance, you can replicate it to other collectors, right? And then you can correlate this very same traffic to BGP, right? And then this traffic correlated with BGP, so it's flow information plus BGP information. It can be aggregated in different ways, and it can be sent to flat files aggregated in some way, and aggregated in yet a different way. For example, it can be sent to a MySQL database, right? And then still with the very same BGP peering, so with the very same BGP data that we are using for correlating the flow traffic, the BGP messaging itself can be sent to in a JSON format. It can be sent to a Kafka bus, right? So this will enable to do analytics against the BGP, right? So for example, you could see from this, I don't know, root hijacks or flapping and things like that. So there was a slide before where I was mentioning that PMACCT can ingest data into a number of open source relational databases and things like that. And at some stage I also mentioned brokers, so Kafka and RabbitMQ, right? So what is the real use case for those brokers, right? So the use case would be to get access to a number of databases. These are, so some are mentioned over here and are, some of them are very well known, like for example Elasticsearch or InfluxDB, right? And so the idea would be that all of these databases, they have modules to ingest data from a broker. So PMACCT has a support for a Kafka broker. These databases have support for a Kafka broker. So essentially, through this middle piece, you can ingest the data from PMACCT into these databases. And we have a slide slightly after on also the reason why we have this middle layer over there. And the other good thing is that once data is in these databases, so Elasticsearch, Cassandra, Druid, Prometheus, InfluxDB, OpenTSDB, but many other, I mean PrestoDB is another one that is left out of this slide, then data can be very easily explored by topping some open source free UI framework like Grafana, like Kibana, or like Airbnb Superset, right? So that is also very interesting compared to relational databases where there is no tight and good integration between, the database and the UI framework. There is a little bit of a special case for Elasticsearch. So as I was saying, you can go through a broker, but there is also this other project PMACCT to Elasticsearch that now is in its third version, let's say. It is developed by another Italian guy, Pier Carlo Chiodi, and essentially this project enables you not to go through a broker, but to either use memory or files, right, over here, to ingest the data into Elasticsearch. So instead of going through the broker, you can use either a memory table or a file. And so the project is also open source and free, and it's on GitHub, and this is the URL on GitHub, so you can check it out if that is of interest. So those would be some use cases by, of PMACCT. This slide would like to convey you the idea that you can do a lot of things with the PMACCT, and let's say you can do a lot of things. There are a lot of use cases covered. The tool is flexible. With flexibility, it comes also complexity, right? The learning curve for PMACCT, I would say it's a little bit steep, but there is a wide community. I am always very glad to help. So in case you want to use it and you bump into some issues, you can always fall back on me. I would be super glad to answer any questions, help you in any way possible. And so since we are here mainly ISPs and IXPs, right? So here would be the top use cases for both category, and then on top of that, so for example, for IXPs, a typical use case would be, feeding, collecting a MAC address to MAC address, so that then you can build a customer portal and you can, show your customers how their traffic is flowing, to which peers, to which of their peers the traffic is flowing. And then, of course, there is, a lot of, use cases that are common to all the different, players in the industry, and that would be like PMACCT as an enabler for triggering alarm, for building historically the disinformation in third-party tools, right? So some non-technical facts about PMACCT, like it's a I would say it's a very old project, like it's more than 10 years that I'm running it. It's actually since 2003, so we are very close to be 15 years. It's from when I was, working for the local university in Bari, where I am from in Italy. And unfortunately, it comes with this very bad name that, I'm for sure I'm not good for. So it's free, it's open source, it's on GitHub, it's independent, right? So all of these years that I've been working for different players in the industry, the roadmap or the development never stopped, and it was never influenced in a way or in another. It's under very active development. So if, for example, you go on GitHub, you will see that the latest commit was today. It was like from last night. Innovation is being introduced, and there will be some examples later about what kind of innovation, what is the current innovation being introduced, and it's very well deployed around the service provider and IXP community. So there are also very large players that are using the software for their flow collection or BGP collection and things like that. Should I mention somebody in the the IXP industry. I would mention definitely D6 and France IX. Of course, I'm not disclosing anything private here. I mean, this is based on public presentation material available on Google. I have to thank, specifically D6 because they were very helpful in the recent years with the PMACCT development, finding bugs, and giving a great feedback from their experience. And if I should mention somebody from more the service provider industry, then I would definitely mention NTT itself, NTT Communications, but also Netflix, the likes of Netflix, Spotify, KPN as another carrier, but also Cisco Systems. So they are integrating PMACCT in some of their products. And so as a last remark, so I am, from the service provider, from this community myself, and so I try always to anticipate and meet the needs of the players here. So you will find all the features that, could be of interest to a service provider or an IXP. So, I would like now to go a little bit more into the architecture and the benefits of using PMACCT after this introduction. And before continuing, I would like to have a question for you. So is anybody collecting, can raise their hands who is collecting NetFlow today? So are you collecting NetFlow? Are you analyzing your traffic data somehow in your network? So we have 2. Okay, very good. Great. And okay, so some facts about PMACCT, let's say architectural facts. So it comes with the an abstraction layer in the middle, so it has flow. It's very easy to in a new backend, new database, be available. It's also very easy to new database be available. It's also very easy to integrate that. So also, like I was trying to say before, let's say 2 things are possible with PMACCT. Like you can, first of all, correlate the different data sources, like flow telemetry, BGP, BMP, IGP, and streaming telemetry. I mean, you can combine them. In different ways, and you can combine to this information also external information through maps, and you can have one big record, one big tuple correlating all this information together, going to the backend. But at the very same time, you can also take all of these data sources in a separate way, so that you can do analytics against each of them. So you can really, for example, keep the flow or augment the flow traffic with BGP, but at the very same time, as I was saying, you can also log the BGP itself, right? And you can do it in 2 different ways. Like you can stream real-time, information to the backend, or you can dump at regular time intervals. So let's take the example of BGP. If you stream it real-time, you would really see the BGP messaging in as JSON objects going, to the backend to a Kafka broker or to files, or and you would really see that, and that is to cover use cases like security, or like to spot if there are root hijacks or flapping and things like that. Or you can dump it at regular time intervals, and in that case with BGP, what you would see is that the routing table or the lock rib of a router would be, a specific set of routes, right? So you will not, that is, you don't see what happens in that time interval, but you have some snapshots at what happens in that time interval. See what happens in that time interval, but you have some snapshots at regular time intervals, right? And that is enabler for different use cases, not from security, but for example more analytics like see the route coverage from understand why at midnight some traffic started flowing in a different way, and for example you can see that that's because a route was withdrawn by was absent, a route that was there in the morning, maybe during the night was withdrawn by one of your transit provider, and that is why traffic shifted from transit A to transit B, for example, right? So different use cases for, dumping at regular time intervals and streaming real time. This is the architecture of PM CDT. So you see, you would have, the network and all the inputs coming from the network over here. They would go in this, so-called core process. So this core process has, several threads. So for traffic, for BGP, for BMP, right? So all the network-facing things of PM CDT are in this core process, and this core process also has this abstraction layer that separates, the backends from the network part, so that you never have an issue, like if you want to implement a new database to know anything about NetFlow or SFlow, and vice versa. You want to implement a new protocol, you tap it into the abstraction layer, and you don't have to know anything about databases and things like that. And those things regarded, so here that are mentioned are as pipes. So it's like the core process is feeding the plugins, and the plugins are instantiated by the configuration. We will see the configuration in a little bit. And these pipes could be, so there are two kind of pipes here. So one is something more homegrown, that is the default one that I developed myself, like in 2003, 2004. It's really a very dumb circular queue in which information coming from the network is put and fed to the plugins. But as a circular queue, it has a fixed size. You have to determine the size of the queue, and if you have spikes in traffic, it could be challenging, because then you may have, you may experience some data loss. Of course, PM CDT would tell you if there is any data loss, so you have to over provision this pipe, and you have to put a number and things like that. So it could be challenging sometimes, especially in very large networks. And then the new kind of pipe that is in there, it's a zero. It's basing on the 0MQ library, and the 0MQ library is fantastic. First of all, because it's super fast for passing messages without a broker inside an application. So it's also open, it's free, and it has the beauty that, of course, it can scale up to the resources of the system, right? So either you can give it a high watermark, or otherwise you can say, for how much memory there is in the box, you can, enlarge this queue. And by doing this, then you have to determine much less parameter when you are configuring PM CDT, and so you are also able to absorb the spikes of traffic that are coming from the network. And that is very important. Imagine that, PM CDT could be exposed to, denial of service, right? Because denial of service is traffic, so there will be a surge of NetFlow or SFlow or anyway sampled information from the network, and so PM CDT should be also able to handle that. So having this new technology is of great help. And then you see that there are the plugins. You have as many plugins as there are the supported backends, so you have also Kafka plugin and things like that. And then the plugins are the ones that write or purge data to the backend. With PMS CDT, I mean, you can build multiple views out of the same traffic, so you can collect your net flow or S flow once, and then you can send it to, so you can aggregate, you can leave it totally unaggregated and send it to flat files, or you can aggregate it in a way that you can build a traffic matrix. So for example, here you have this aggregation like ingress router, ingress interface, BGP next stop, peer destination AS, which is, you know, the essential tuple that tells you, you know, who is injecting traffic into your network, what is the ingress point, what is the egress point, and who you deliver traffic to, and that is the essence about the traffic matrix. And then of course, I'm already speaking about aggregation or no aggregation. So of course, networks today, they spit out a very large amount of data, and so it is very important to be able to, you know, aggregate this data, filter this data if there is things that are not of interest, channelize this data, and possibly even sample or subsample if data was already sampled before. This would be like, so we now get a little bit more practical. So we have a you would basic configuration, like you give bind to an IP address and to a port, and theoretically on this IP port, and theoretically on this IP address and port, you have your router configured so that it's exporting net flow, for example, to this port and to this IP address. So then what you do is also you instantiate the plugins, right? So you have the plugins lying here with, so in this case we are instantiating two plugins, like a print plugin. Print plugin would be the one that writes to flat files, and the MySQL one, right? And we give it also a name, so we call the print plugin, we call it forensics, for example, and we call int traffic matrix, internal traffic matrix, the MySQL one. And then what we do is that by calling again this name, right, we attach further configuration to these plugins, to the specific instances of this plugin. So we define an aggregation method, right? So you see we have two lines called aggregate. One is here, I'm pointing on this screen, and the other we have underneath here. And so those would be the aggregation methods for the two plugins, right? So the one for forensics and the one for internal traffic matrix. And what you can see is that in the forensics one, you have a very long aggregation, or you can call it a deaggregation method. You have E-type, so the Ethernet type, so you know whether it's IPv4 or IPv6. Then you have the source host and the destination host. Those would be source and destination IP addresses in the flow record itself. Then you have peer source IP and peer destination IP. It's a little bit PMS CDT jargon, this one, but they would be the ingress router and the egress router being the BGP next stop. Then you have the input interface and output interface. Of course, these are related, they are relative input and output interface at the ingress router. Why at the ingress router? Because that is the router that is exporting the flows, the actual flows. And then you have the start and the end of the flow itself, source and destination port and protocol, so that would be like TCP or UDP and the TCP and UDP ports. And then you have type of IP type of service, source mask, destination mask of the source and destination IP addresses, source autonomous system, destination autonomous system, which would be the autonomous system of the source IP address and of the destination IP address, TCP flags, and for example the sequence number number of the NetFlow packet, so to see that you are not missing out on any packets. So this would be like as raw as possible you can go. So like by doing this, you are essentially writing to the disk every single microflow that is flowing through your network and that you are exporting by NetFlow. So all of those you are really writing to a file, right? And this is, for example, why this plugin is called Forensics, is because maybe somebody tells you like that you are producing a denial of service and you want to know how this denial of service is traversing your network, right? And so you go back in the flows, somebody can tell you like this IP of mine is being attacked, but I have this spoofed source IP address, and then you can go in your network and you can check and you can see what is the ingress router, right? You can see the input interface, you can see whether it's one specific of your customers that is producing that, or whether you are transiting from somebody else, of course, if you have downstream customers, right? Or otherwise you will be able to pinpoint to your specific port where this denial of service is coming from. It's much more traffic matrix, right? So in traffic matrix, right? So input interface, ingress router, egress router, and peer destination AES, right? So you can intuitively think that if you have 1 million flows and you have 10 nodes, for example, 10 routers in your network, you will bet that more or less this, as a result of this aggregation, you will send to MySQL, let's say every 5 minutes, you will send, 1,000 records. Whereas, as part of this very deaggregated view of the traffic, you will write down to the files the full 1 million records, the full 1 million flows, one by one, right? So that is essentially also a little bit the powerfulness of, data aggregation. The fact that you build a very specific data set to what you want to accomplish. So another thing that you can do with the configuration is essentially, you have data aggregation, but then you have also, let's say, you can define primitives, traffic primitives, right? So imagine that NetFlow and the S-flow, they are very generic transport protocol in which you can export traffic flow, but whatever else. So for example, you can export as part of NetFlow also MPLS information. So the labels of the traffic and how it is labeled, what is the MPLS stack and things like that. So from that you can derive which VPN traffic is and things like that. So this is something that is not supported natively in PM CDT as a primitive, right? But fortunately what you can do is that you can define your own primitives, right? So there is a full framework where you can, define it. So you point PM CDT to a file containing the primitives. This is how you define them. And, the way in which you define them is very simple. I mean, you give the new primitive a name, and then there is, through your vendor specs or through some sniffing of the NetFlow, you can determine what is the field type, the length, and the semantics, right? So what you need is really, give it a name, know what is the field type. That is something that your vendor has to give you. It has to give you, a table, like, my NetFlow exports these records, and these records have this format. And then essentially from there you can compile these other 3 fields. So the field type, the length, and the semantics. So by doing that, you can expand PM CDT even beyond what is already supported out of the box, and introduce new primitives to do accounting of things that are very specific to your environment. So two examples in this sense are like one I I already mentioned, like MPLS, like there is people that, there are organizations accounting on MPLS and seeing how that performs the traffic inside the different VPNs. But again, we go back to the security, like all the vendors, like let me mention, for example, Procera, right? So they have these firewalls that they can do also NAT, they can inspect the traffic, they can do deep packet inspection and things like that. And they export a very specific kind of net flow. So they give you the specs of how the records are composed, and you can define all of these primitives in here so that you can account on, for example, firewall events or NAT events or deep packet inspection events, which is something that is not natively supported by PM CDT. So, checking on time, okay. So, as I was saying, PM CDT has a BGP integration. So, in the next few slides, there are, all the different integrations that are in PM CDT that are supported. So, one is BGP. I was mentioning it several times. So, essentially, in very essence, PM CDT supports all that should be supported by an implementation in 2017, so 32 bits ASNs, ADPACT, and things like that. So when you let PM CDT peering with your device, it is not going to advertise anything to your routers, right? So it's going only to receive and really the code to send a BGP update. It's not in PM CDT, so it's pretty safe, and there are large networks that are relying on this. And of course you can count also, I am very active at ITF as well in the IDR and GROW working groups, so you can always count that the latest draft are implemented. Now, not mentioning BGP ADPACs, but for example you have large communities, you have BGP shutdown, it's everything in there. So also, let's say why having such an integration in the flow collector? Essentially for two main reasons. So one is because you imagine you have a lot of routes and a lot of flows. So it makes sense to combine this information as part of the same software package, because if you collect the two things in a separate way, then reconciliating them could be very computationally expensive kind of job, right? Going and post-processing files and doing this reconciliation. So that's why it makes sense to have both information as part of the same collector. And the other thing is because you never would like to have BGP information being put as part of NetFlow, right? So combined in NetFlow as part of the router, because there would be a lot of redundancy, right? A lot of duplication, a lot of the very same information repeated over and over. So actually putting, having a BGP integration within the flow collector makes a lot of sense, because it gives the good trade-off between the good balance among the different elements. So there is a BMP integration. So BMP is a BGP monitoring protocol, and this was written from scratch, whereas the implementation was forked by Quagga many years ago, like in 2008. Different from the original code, but still I should mention that. So the BMP did the original code, but still I should mention that. So the BMP daemon, it's written from the scratch. So BMP is a great invention in my opinion. It's it's a protocol to monitor BGP. So it's coming out of ITF. The basic part of the basic implementation of BMP has been already drafted and standardized, and there is some activity today to make the same possible for. So it's like today PMP supports only add rib in, so the rib from the input rib from the neighbors that are from the BGP neighbors connected. But let's say there are two drafts to also support the local rib and add rib out. Add rib out will be intuitively the rib at the moment in which you are, advertising information to the BGP neighbors, and the local rib would be the closest of what you can get, like with a BGP with a real BGP peering. But the nice thing with BMP is that you don't really have a BGP peering, so it's a very nice, let's say, separation between, protocol like BGP, that is, the control plane, and the monitoring plane here. So then there is IGP integration. So there is only ISIS is supported. It's not supported OSPF at the moment. And as you can read from this slide, it's very limited support at the moment. So the only use case that is supported by now is just looking up some routes, like so doing really route lookups that are not in BGP, for example. But the idea is to replace this IGP integration with the BGP-LS, which is much cleaner, much standardized. It is actually standardized compared to just this integration here. But also the other good thing is that with BGP you have the nice separation. So with BGP you can enforce policies, for example, right? In the IGP, it's, let's say, it's much trickier to try to do that. So methodology, right? Just to would anything go wrong? Like with BGP you can say, like, okay, would anything go wrong? To would anything go wrong? Just to would anything go wrong? Like with BGP you can say, like, okay, you can set policies on your router and say, like, you are, PMACCT, I will not accept it. But with the IGP it's much more difficult. So it's GP is much more difficult. So it's good to transition from the IGP integration to BGP-LS. And BGP-LS stands from link state, so it's a way to action. So IGP protocol information over BGP. No. So going to the storing data persistently, so this is, I will go a little bit quicker because it's, let's say, I've already said before. When writing, especially flow data to the disk, it's very good that things are aggregated in the spatial and temporal way, so that you are somehow limiting, the data set, and you are not building huge data sets of gigabytes or terabytes that then maybe you have to reconsolidate because you are writing every microflow to the disk. So you want to consolidate them in memory and then write a very lean data set that is matching your needs. And so when doing that, so when writing project-oriented data sets, let's say, so of course what can happen is that you have the same information written a few times, in different data sets. But there is no real shame in that, because let's say if you consider that you have, let's say, three components. You have CPU, memory, and disk, right? Writing a very lean data set for your project, and maybe if you have 5 projects writing 5 different data sets, maybe in the end you are burning more disk space, so you are not optimizing on that, but the computing, so the CPU, more expensive resources. So staying still, what are the two options of storing data? Of course, you have files, right? So I was mentioning that before. But let's say what would be my two recommendation would be either to go with a relational database or with one of those NoSQL databases, which are at the basis of that marketing term called big data, right? So these databases that would be the ones that I was referring to, that they could be accessed through brokers. They are, the good thing in them is that they are modern. They are UI ready, like I'm saying here. Like you have the ELK and the tick stack, so Elasticsearch, Logstash, and Kibana, and you have the equivalent for InfluxDB as well. So essentially, you can do, you can store much more data. You can handle much more data. Of course, this doesn't come for free. Like you can imagine that NoSQL databases, they are worse in doing relations. Most of them can do just time series, and they can do just time series and then exploring and doing some operations on the time series that they are there for. I mean, they do it very well, very fast. And since many of the projects can be reducing time series when collecting flow data and when speaking about traffic matrices over time and doing snapshots every 5 minutes, for example, then the NoSQL are very fitting this problem space. MongoDB was actually it was mentioned on one of the initial slides, and it was like a PMACCT opening many years ago to the NoSQL databases. But let's say this is going to be discontinued because of lack of interest. Because one phenomenon in the NoSQL databases is that they are being recycled very quickly, right? So there is a lot of new products coming on the market, and then they kind of become if not obsolete, there is new technologies always coming up, and then you feel that those older products are not mentioned anymore. Maybe they are even abandoned or not developed and things like that. So we already went through a few cycles, right, in the NoSQL databases. This is not the case for MongoDB. I would say only that people are totally looking into Elasticsearch and Influx and Druid and those things, and I don't hear anymore from the community any interest in MongoDB. So let's say there was the choice for MongoDB many years ago. It's because it was offering grouping operations, and it had the concept of sharding. So it was very interesting for horizontal scaling of the database. But that's why it was preferred to other. But that's also why I was speaking about the brokers, because the NoSQL movement, let's say, it's very difficult to move through, because there are it goes at a very quick pace, that there is new databases being rolled out, and so you cannot really follow and track and implement all of those. And that is why we have in the following slide so the reason to go for brokers, and so because I really stress it yet again. It's imagine there has been times in which every 2-3 months there was a new database coming out, and now it was Facebook, and now it was Google, and now it was somebody else, and they were all inventing a new technology. And then you imagine the community then comes back to me as a developer saying like, hey, it would be very very nice to have this database implemented, and then after 3 months it would be like very nice to have this other database implemented. So having the brokers in the middle, so the Kafka and the RabbitMQ, it's kind of a way also for me and for the PMACCT project to give access to all of these databases without having to implement each of them in a native way. So I should not become super expert of every API of every NoSQL database. So having this piece of middle, in the middle, that is also, so it's natively, so a Kafka broker is natively supported by PMACCT. It's also natively supported by these databases. So there is a very good integration, and it's benefiting pretty much everybody. So let's go to the example with the traffic matrices. This would be very close to what I said already the other day. So there are pieces in which I will go pretty fast, and others, I mean, that I will spend a little bit more time. So first of all, yeah, traffic matrices, are they important? Are they an important topic? Yes, because many of the decisions that when you do, discuss peering, a lot of decisions, they go around traffic, right? The traffic and traffic amounts and things like that. So having a traffic matrix, in other words, having a traffic visibility into your traffic, it's very important to support your peering decisions. So who you want to peer next, which is the peer you want to really chase, what is important, where is important to go, or for example, the same goes for the transits, right? So sometimes you want to determine if you have 1 or 2 transit, if you want to replace one, or if you want to add another one. I mean, everything comes from the data in the traffic matrix, right? So if you are not analyzing and you have not a visibility in your traffic today, this is something that you should really consider doing. So a review of what is a traffic matrix. We have, let's say, 2 kinds of traffic matrices. There is the internal one, and the internal one would look like this. So what is essentially the internal one? It's a node to node. The internal traffic matrix will essentially tell you that there is traffic from this node, or so it's internal to your network, It doesn't say anything about the ecosystem around you. So for example, about your peers, or about your transits, or your customers that are running BGP. And this would be instead an external traffic matrix, right, where essentially you have this extra information. So you can consider, that you have all that extra information as part, of the traffic matrix. So the traffic matrix will be richer, it will be bigger in size, it will contain more tuples and things like that. So so we focus on the external traffic matrix. Why? Because this is a peering forum, and so we need information about transits, about peers, about customers with the BGP. And so, as we were seeing, the internal gives only information about our network. That is very good for traffic engineering and capacity planning internally to the network. But then in the external traffic matrix, you have also information about your peers, your transit, your customers, how you are fitting in the picture, how traffic is flowing through you, and things like that. So shall we translate the external traffic matrix into PMACCT into PMACCT jargon? So let's say that we have, again, this is our network, right? And we are transiting some traffic flows, right? So we have the yellow, the red, and the violet one. It's that violet? It's that, yeah, it's violet. So let's say that we have 3 flows, right? Here, we have 3 traffic flows. So the way in which you would configure the traffic matrix in PMACCT is like this one, right? So we have, yet again, the same information like I was mentioning before. We have the source AS, the input interface, the ingress router, the egress router, the AS path, some timestamp, time reference, and bytes, so a counter. And essentially this is how the flows would look like, right? So if you would pick the pieces from this picture, from this diagram, and you would replace these primitive names, and you would give a name for each of the 3 flows, this is how they would look like, right? So this is maybe a slide for later, for reviewing the PDF and things like that later on. And you see there is this bracket. You have like this little bracket in all the 3 flows, right? So there is essentially, that would be the source PRIS. So that would be the autonomous system that is injecting traffic into you, right? So imagine that you are you are dominated by inbound traffic. That would be your transit provider, for example. So that is not part of the primitives. So you don't have this information as part of these primitives over here. And why is that? Is because this is a derivate kind of information. So you have the input interface, you have the ingress router, and then you should compute somehow, that this autonomous system is connected to this port, or if there is, that port is facing an internet exchange, you have the source MAC address, and you should say this specific MAC address is injecting traffic into me, right? So it's kind of a derivate information, and PMS CDT is not going to do to give that to you. You can inject it through external information, but through a map, for example, but this is a part of the puzzle that you have to fix yourself. So getting BGP to the collector, do you really need BGP? Only for technical or a few non-technical reasons. So it depends essentially on your net flow. If you don't have the BGP next stop, or if your exporter is not aware of BGP, or if you are using libpickup to collect the traffic data, so you don't have any control plane information, or in cases in which you are transiting, so you have downstream and upstream, you have upstream providers and downstream customers, or if you are dominated by outbound traffic, like you are cloud, data center, or content delivery network and OTT and things like that. But for the specific case in which, for example, you have your routers exporting at flow v9, you are dominated by inbound traffic, and you have 0 downstream customers, like you have only eyeballs, then essentially you don't really need a BGP peering for your traffic matrix. How you should, theoretically, in a model in which you want to build a traffic matrix, and you need BGP, how that should be done? You should really all the PE devices, the provider edge devices, so that are facing peer transit and customers, they should connect with the BGP peering to PMS CDT, right? And so you can count some like 50 megabyte per full routing table, per session, and that would total like to 9 gig of memory for 500 peers, and 500 peers are a lot. 500 nodes, it means world scale network, right? So imagine that you have 100. So imagine that you have 100 like 2. So as I was saying, is facing transits, peers, and customers. You should configure PMS CDT as a route reflector client. You should have facing transits, peers, and customers. You should configure PMS CDT as a facing transits, peers, and customers. You should configure PMS CDT as a route reflector client. You should have so one PMS CDT can, if you have multiple autonomous systems, or you have sub ASs, so you are confederated, your network is shaped as a BGP confederation. I mean, one PMCCT can hold all the peering, no problem with all of those, even if they are in different autonomous systems. And the BGP next stop has to represent the remote edge of the network, right? That is very important. It has to be the egress router. This is the typical case with, this is very typical in every MPLS network, for example, it's just like that. But it's just a noting case. For example, you have routers with partial views and a default, or you have BGP confederations. In that case, you have to do something that I determined there, like a follow-up. Like, so you have, all the routing tables, and in PMSCCT you can define, oops, sorry if I wake somebody up. And then so essentially you can follow it up. So imagine you have all the routing table from all your nodes, and imagine that one of those or some of those have only a default route that is pointing to one of the ones that have the full routing table. So essentially with PMSCCT you can do these follow-ups so that then you can determine what is the egress node. So then you should get the telemetry to the collector, right, to build PE devices. And so why ingress only? That's why you need, that information, so that then you can correlate with your infrastructure data, who is connected to which interface, or which of your peers at an exchange has which MAC address, and so essentially you can correlate all of this and complete the information and determine who is the adjacent autonomous system that is injecting traffic into you. So this is how BGP telemetry and NetFlow would work in PMSCCT, how the correlation works. It's a process in 4 steps. The first step is, imagine again this orange circle here is the observed network. Step number 1, the edge nodes, they are, sending BGP tables to PMSCCT. Step number 2, there is some traffic flowing through, right? So there is a traffic flow from source AS to destination AS. This traffic is passing through your network, for example, and this is triggering step number 3, which is the NetFlow record being generated. And then as a 4th and last step, what PMSCCT does upon receipt of this record is going in the BGP table received from that router and checking whether it has, entries for the source and destination IP address. So how do you configure PMSCCT for a traffic matrix? We did already see it a little bit before, but in this example we have, you remember before we had forensics and internal traffic matrix, now we have internal and external traffic matrix as examples. And so you can review the 2 aggregate lines, right? They are different for the internal and external. The external, it's, de-aggregating more, as we would expect, compared to the internal. So it will produce more tuples when we go and we write it to the disk. And so what you can see here is that we are configuring so this example is based on relational database, but you can, you can map it the same to files or to whatever else. Essentially, you see you have a dynamic, or you have a file, a table name, an SQL table name with some variables, and those variables are time-related variables, right? So it's like every snapshot. Imagine that you do snapshot for your traffic matrix every 5 minutes. Let's say each one will be put in a different table, so where they will not be compounded in the very same SQL table. So you can do easy exploration within a traffic matrix, but then you will have to do joins and things like that if you want to explore, across, different snapshots. Of course, nothing prevents you to put everything in a single table, but putting it in different tables allow you to scale more, because there is that many tuples that a relational database can insert and explore at as soon as you reach the million of entries, then you need a lot of computing power to quickly explore those. Of course, another option would be to use, instead of a relational database, to use a NoSQL database, right? And so in that case you can put much more information in a single table, and you can do also exploration across snapshots across times, right? And so what you see here, so it's the table name, variable, amount of cache entries, because if we are doing snapshot like every 5 minutes, like you see here, so the PMACCT has to cache the information for 5 minutes, so you have to say how big you want the cache. Typically, it's the default settings are okay, but at least for a traffic matrix, it would be different for logging microflows, but this is an information, and then you have the rest of the configuration. This is how things would look like then in the database, right? So this is the set of tables, you see. I was saying that with that configuration, PMACCT would dump every 5 minutes information in the database, and the table name is dynamic, and here you have, the table name composed with the time. So PMACCT will write, will determine the time at the moment and fill the variable, the time variables, right? And so you have the internal traffic matrix, external traffic matrix, those are all the tables in the database PMACCT. And then this is how things would look like inside each table, right? So this would be our traffic matrix, right? So it's like we have the input interface, we have the ingress router, we have the egress router, we have the peer destination AS, so the AS we are sending, the agent AS we are sending information to. We have time reference, like it's 2 p.m. of this date, and then the amount of bytes, right? So in the end, this is a traffic matrix. So applying this to when I was at KPN in AS286 in 2009, so this is how we were doing peering, right? So we were seeing peering as a cycle. So we have negotiation, then we have engineering of the peering. Like so, the peering coordinator will go to the engineering department and say, look, we have to do this. So provision. So we need 10 gigabit in that city for that kind of for peering with that party and things like that. And so all the magic happens. So the BGP is configured and capacity is added. Even capacity on the core is added if that is needed, right? So then the thing goes in production, right? And then in this stage of the production, with NetFlow, we were evaluating, if capacity is sufficient, we need more capacity. We are, analyzing the traffic distribution. Are we already at 80% of the peering with somebody? We are peering at an internet exchange with many peers. We can analyze the traffic per peer and see whether we must take that specific peer off of the internet exchange, right? So imagine that you have a 1 gig port and you are exchanging 800 megs with just a single peer. So you would go to a private peering maybe with that one, and then because it's monopolizing your IXP bandwidth. And then we have the optimization phase, which is precisely as part of this analysis, go back essentially to the peering coordinator and input the peering coordinator with information with all the red flags or the white or the yellow flags, and say, hey, we have this and that problem. And so the next round of a negotiation goes on. So the peering coordinator goes to a peering forum, and it will negotiate, the new peerings and what's going to happen. So peering as a cycle. And back in 2009 at KPN, we were using NetFlow to PMACCT, and then we were storing this data in a MySQL, and then we had internal users that they were either exploring this data through a UI or we were building reports. And back then, I mean, this is the specs that we needed. I was running Spark process over Spark processors, Solaris, and you see those would be the specs, and the vast majority of the specs is taken actually from MySQL and not from PM CDT. Some tips, when you do peering as a cycle, maybe what you want to do also is define templates from which you configure your routers. I mean, this is something that you should do, in my opinion, anyway. And essentially, when you, as part of the template, you have exporting a net flow to the collector, and then essentially this is the enabler for auto-discovering new devices. Right? Because then you deploy the router, it's starting exporting net flow, and from data you see that a new node is in the network. And then of course edge interfaces are provisioned, service delivery manuals. So when you should really ensure, it's very typical mistake that you provision a new customer or you provision a new peer and things like that, and the engineers forget about enabling a net flow. So then the peering coordinator is looking for information about some traffic, and the net flow was never enabled. So this is why you should have, provisioning manual for interfaces so that your engineers do not forget about net flow. So we have this other example about logging microflows and events. It's 12:30. We started, half an hour late, so I will go on. But if you want to go on lunch, if you are starving, I don't want to. Last thing is to have casualties at a peering forum, so we should prevent that. So let's say brief history beyond this other example. So which would be, so before we were saying aggregation, traffic matrices, now we are saying logging, microflows, so it's security, it's this kind of other use cases, exploring data for things that are wrong in the network and things like that. So brief history, I mean, PM CDT comes really from, databases and flat files, writing to files was never supported and things like that. And that was until, even pretty late, like until 2010. You can imagine, like, the project was going on for even 7 years without being able to write to flat files. So why was that? It's because, there were other projects doing that, flow tools, NFDump, right? So what I was thinking is why I should, enter into that specific thing when I can spend my time in doing new and cool stuff, right? So that's our objective in life, do cool stuff always. That's but in 2011, 2010, 2011, I started, to do we opened PM CDT to flat files, and actually was for a cool reason, and that was because NetFlow, IPFix, SFlow, they are very generic transport, right? So they started with flows, right? But they can transport every sort of information you want, right? It's in the end, it's protocols that implement TLVs, right? And in a TLV you can put whatever information you want. And so that happened, right? So especially pushed by Cisco back then, NetFlow and IPFix around that time started entering the business of transporting log events, firewall events, and they also tied up, very importantly, NetFlow to NAT, or carrier grade NAT, right? So essentially, it was a great, and why is that? Because you have a TLV, and it's a structured format, and it's a very good way to transport something like a syslog event that is, just text, right? So imagine that you can have a TLV with the severity of the event, and then description of the event. Suddenly you have everything without having to parse specifically the syslog event. So So okay, so it was a great time to review this strategy because all of this was happening, and with that massive scale of information, back then you couldn't store all of this, in a database, and the NoSQL databases they were very, very new thing. Nobody had them in production, and so it was a great time to review the strategy and open to flat files. So what would be the use cases for files and for logging? As I was saying, research and development, lab activities, security, DDoS detection, forensics, or also because imagine that you are in that very first stage in which you are collecting NetFlow data, you don't know yet what you want to do with it. So first you want to see which data you have, and then from there you want to build, your data set for your project, and maybe you want to estimate what will be the cardinality of, your data set, and so that's why you have this kind of let's say information. So that would be temporary or also permanent. Let's say you want to have that information just in case, just to, because people know that you are collecting NetFlow statistics, and people in your organization, like a product manager, and then they want to have a query or an exploration that you didn't think of. So you keep this raw data, maybe for a day, maybe for 2 days, right? Not very long, so that then if somebody knocks at your door, you can still be the superstar of the day, and you don't say that I don't have this data, I don't know how. We have logging use cases. This is why microflows. This is why microflows. Cases. This is why microflows. But events, for NAT or firewall events or syslog in general. Very similar, to what we have seen before with the SQL tables. Also here, what you can do with files is that you can have split the data into different files. You can, have also a directory structure, and you can split this by time, by flow exporter, or both of them actually. So you can, of course, append to an existing file. So what that allows you to do is essentially to have 5 minutes files, but for example refresh them every 1 minute, every 30 seconds. So you can append so that you have always very fresh information in the file, but still, for example, you want to do time binging of 5 minutes, and so you can have that freedom. And the print plugin of PM CDT, which is the one that allows you to write into file, supports triggers. So essentially what you can do with the trigger, so you can trigger an external script, and with that essentially pretty much real time you can, once you are finished to write to a file, you can compress it, for example. And then you have the nice feature that you have a pointer to the last, what? To what? Slow. Oh, okay. Okay. So, thanks. Sorry for. Okay, so then essentially you can essentially you have triggers, so you have the possibility to compress data pretty much real time, and then you have also the feature of pointer to the latest file in in the set. So right, you have a time series, you have the pointer to the last, so that you can always access very easily the latest data. So the data formats supported are tab-spaced, CSV, and JSON, and I would say each of those come with the so those are the text formats, and then we have the binary formats, and what is supported is Apache Avro. Each of those have pros and cons. Like there is not a definitive winner. Like CSV, it's the maybe simplest serialization method, and it's as a result of that, it's also the quickest to serialize. But at the very same time, it's not self-descriptive, right? So you always need a title in order to make sense of a record. And that is a very big downside for CSV. JSON, on the other hand, it's very verbose. I mean, it will really add to the disk space that is needed, but it's always true that you can compress it. So it's also slower to serialize, but as the good thing that it's self-descriptive. So every single record, you can just get a record and you know immediately, which fields, so you don't need a title. You can do everything with a single record. In terms of binary formats, so PMACCT CDT never decided to, as a project, to implement their own binary format because, I think there is people that do this kind of stuff better. So I always wanted to rely on, people doing the good things. Of course, you have a few options over there. You have Google Proto buffers, you have Captain Proto, you have Avro. So I went with Avro because it's Apache Foundation. So if you tell me always, one of the greatest evil in the world, Google versus Apache Foundation, for me it's it's of course winning Apache Foundation, and when I say greatest evil in the world, it's just because there is, of course, it's a company and it has an interest to push their own product and things like that. And then I think we should go for something that is more independent, something that is more supported from the community and things like that. Let's say Google Proto Buffer was avoided. Part because it's from Google, and part because it comes with this concept of schema, and with this concept that you have to embed code into your software, and that is code produced by a compiler from Google. And I thought it was not really, and that is for serialization and deserialization, and I think that that is not the best approach to do it. Whereas with Avro, still you have a schema, but the schema is part of the, for example, header of a file, and then through the API, the Avro API, you can serialize and deserialize. So I found it very clean, very good approach. Captain Proto, actually it's another serialization method, a binary format, that is developed by the author of Google Proto Buffer, but the guy left Google and made this new format. I heard very good things about it, but for now, it's not supported. Yeah. So this would be a configuration for doing forensics, for example, right? So you have the print plugin, we give it a name. Again, we have the aggregate, we saw it before in the example before, very long aggregation method. So this is the aggregating a lot, this is producing a lot of tuples. And then we give it, like for the SQL table, a path and a file. The file is dynamic. We give it a format like CSV, and we say every 300 seconds to purge this data. We say to do time binging of 5 minutes, and we say to append, right, files, and then we say also, we specify what should be the latest file. So we want to call the latest file in the series forensic latest, and this will be linked always to the latest, file in the time bin, in the time series, sorry. So this is how things would look like into let's say into the directory. You have the files, and you have again the time, 1345, 1350, 1355, 1400, and things like that. And this is how things would look like, inside the latest file, right? So we selected the CSV serialization, so we have the title, and we have the information in here, right? and then the multiple lines, it would be all one flow per line. This would be, a configuration snippet to log NAT events, for example, and you have again here, NAT events for carrier grade NAT. So you have again the print plugin, you have the aggregation method, again all the information about the file, the format. This time we are saying JSON, just as for fun to see the difference with CSV. To purge this data every 300 seconds, 5 minutes time binging, very large cache, append files, append 2 files. So again, this is how things would look like in the directory, and this is how things would look like in the latest file. You have this information, it's JSON format, and it's nice, and it's self-descriptive, and things like that. So so imagine that you have these two use cases. Yes, it is possible to combine the two things, but I would not recommend it for very large deployments because you can be imagine that you are doing syslog and flows with the very same PM CDT, and you can have a lot of syslog coming, for example, and also you can be exposed to a DDoS, and so you would have two pressure points onto the collector. So I would say you could combine the two functions that I just described, but split them. So this would be how to write a configuration for a combined collector for logs, for syslog and for flows, and this is only wants to tell you that essentially you have here you can filter and you can channelize traffic with the PM CDT. So for example, you can define tags, and tags are in this map like here. You say if it's flows, tag it with 10, and if it's an event, tag it with 20, right? And so if we go back to the configuration, then you say all the tuples that are tagged with 10, then they go to the forensics plugin instance, and if they are with 20, they go to the CGN, so to the carrier grade NAT, so to the syslog event logging. Okay, so the last part, we are close to the end, and you will be all released, and a single collector, of course, may not fit everything, right? Why? Because there is resources constraints. So we have, let's say, memory constraints, CPU constraints. So whatever we are discussing here, which is logging, microflows, syslog, or traffic matrices, it's all things by which essentially a divide and conquer approach is very valid, right? So what you can do is really you can map your routers onto PM CDT collectors, right? So you can do really partitioning, and then you can map PM CDT collector to database nodes and or to let's say to brokers, and if that part is clustered, then it's resolved. So like you just point all the collectors to the cluster, and then the cluster will take care of the horizontal scaling itself. So that said, let's say how you can you do put in place some countermeasures to avoid that the matrix becomes big? Yes, you can do that. So for example, imagine that you are dominated by ingress traffic, then for example you can avoid to account for all the egress traffic, right? And then by doing that, you are already halving the size of your traffic matrix. Other strategies, what would be? It would be like that if you have larger routers and smaller routers in your network, imagine you have a small pop and a big pop, maybe what you are after is the big traffic flows, right? And so the small router maybe will not generate big traffic flows. Imagine that you have 10 gigabit pipes and you have pops with, I don't know, Cisco Cisco 7600 or a big MX router, and then you have a POP with a small 7200, right? So that 7200 maybe will not generate that much traffic, so you can reduce the traffic. And maybe you can, avoid to account for that specific traffic too. So what is the need for horizontal scaling? Now we speak horizontal scaling, so how we can have multiple collectors, right? So we are saying like you want to do high frequency sampling because of security, right? Because, for example, you want to do anti-DDoS or you want to do forensics, and so you cannot have 1 in 10,000 sampling, but 1 in 100 or 1 in 1,000. Also because let's remember that the interfaces are going from 10 gig to 100 gigs, but I'm at least myself not seeing people that are resizing their sampling rate from 1 to 10,000 to 1 to 100,000, right, or things like that. So the sampling rate, I see they are remaining the same, even if the circuits are capable of doing 10 times more of traffic, and that will lead again to high frequency sampling. And then of course again in the case of logging, for example, for NAT events, imagine that you have a carrier grade NAT and you have a router and the blade that is rebooting, you suddenly may have even 1 million sessions being logged in a very short amount of time. So you have a lot of events. So we were saying you can reduce, employ strategies to reduce your traffic matrix, and that is something, to output less data. And this would be, imagine that you have a lot of data, and so even by reducing, by doing that, still PM CDT itself. So PM CDT itself supports a T plugin. T would be like a replication, right? And that is the fundamental part by which essentially you can do the horizontal scaling. So it's like instead of directly pointing the net flow at the PM CDT collector, you add an extra layer in the middle. You point your routers to this T, so to this PM CDT that works as a T, and then PM CDT, so the replicator will be able to send the net flow to PM CDT collectors. Or imagine that you have third-party software as well, then you can send it to the third-party as well. The nice thing about the T plugin, so the T plugin would really map to another software that is in that space, which is Samplicator. Samplicator is there forever. The T plugin of PM CDT does the same and does much more features, and is supported because Samplicator is not supported currently. So, for example, among these features that PM CDT T plugin has on top of Samplicator, you see that you can add, change, or remove receivers, so collectors, on the fly, so without having to restart the replicator itself. You can do, various strategies for load balance the traffic among the collectors if needed, and you can do also selective teeing. So you can say some flows go to one collector, other flows go to another collector, for example. So that is for horizontal scaling, or if you have flows for different use cases, and then you have different collectors. So you have PM CDT, you have Arbor, you have other things, and so you want to send specific traffic to specific collectors. So multiple PM CDT collector can go in parallel, and it's what we were saying before. The important thing is that, for example, if you are exporting multiple data sources at the same time, like flow telemetry and BGP, the important thing is that when you do this partitioning, you also keep all the data sources together. So you point BGP and let's say BGP and flows to the very same partition of the collector. And then this is how you can configure the T plugin, right? So I have here an example for a replicator that is also a balancer. So you define some buffering, and then you say, let's say, use ZMQ, so 0MQ for queuing because it's more scalable, and then essentially you have the list of receivers here, and you say to act transparently, right? So transparently is like that your collector will see the traffic, the net flow, as if it is coming from the original router and not from the replicator in the middle. You have different use cases for both. You can be transparent or non-transparent. Sometimes you don't want to expose, if you are giving flows to a third party, you don't want to expose your infrastructure to the third party, and then essentially maybe what you want to do is to act as a replicator but also as a proxy. So you want to be non-transparent. So in that T receivers list, for example, you can have a line like that. So essentially you see you have a set of IP addresses and ports, right? And then you, for example, here tell also how would you balance among them, right? So if you would not have this balance algorithm here, it would just replicate the same information to all of the collectors that are listed over here, but with this, what it will do, it will balancing among them, right? And what we have configured there is just a hashing, right? So it will see in this case which route, it will do a hashing on the IP address of the router that is exporting the flow, so that consistently you have not round robin, but consistently the flows from the same router will finish to the same collector. This would be a transparent selective balancer, right? So again, we have the very same configuration as before. We have one extra line. This line, so I'll go to the next slide to see what would be the content, right? So we have, you remember, our T receivers list. In this case, we have two sets with two routers, and we have tag 100 and 200, but actually where we impose the tag is here. So we say, for example, imagine that 10.0.0.0/24 is the class that you reserve to your backbone routers. Let's say you chop it in two, you do 2/25, and you say that for the first 128 you want to send to collector A, and the other you want to send to collector B. So this would be, again, a way of balancing, but it's not hashing, but it's selective. So you are tagging, and then you are filtering. And finally, we are at the end. You are about to be released. So if all of this information was not enough and you want even much more than that, of course you can stop me wherever I am here until this evening, or I leave you with other references, right? So with the PMACCT wiki, there is the GitHub page of PMACCT, so where you can star or watch the project, and other presentation to give even more information about what we spoke today. And with that, I'm finally finished. I thank you for your attention, and if there is any questions, you can ask me now or later. Everything is welcome.